Hi guys, this is AS Chemistry, Organic Chemistry, and we are looking at organic synthesis. Question 6. Complete the following reaction scheme which starts with propene. In each empty box, write the structural formula of the organic compound that would be formed. So here is the complete organic synthesis pathway. So we start with product A. So we've got CH3CH double bond CH2 reacting with bromine. So this is an electrophilic addition reaction in which the bromine atoms will add onto each of the carbon atoms forming the double bond. The double bond will no longer exist and we will end up with a molecule of CH3, CHBr and CH2Br. This is the product A. On the right side, we've got KMnO4 and acidified with cold and dilute as the condition. So cold, dilute, acidified KMnO4 results in the formation of a diol. So we will have CH3 bonded to CH on which an OH group will be present, which will be bonded to a CH2 on which another OH group would be present. So this is the diol, that is compound B. Now, when the alkene reacts with HBr, so electrophilic addition reaction occurs, and we end up with two products. One would be bromine placed on the central carbon atom, which would make it 2-bromopropane, or bromine placed on the terminal carbon atom producing 1-bromopropane. But formation of 1-bromopropane would not be preferred. Formation of 2-bromopropane would be preferred. So the structure we'll make here would be CH3, CHBr, and CH3. 2-bromopropane, which is the more stable product. Now, 2-bromopropane on the left reacts with KCN in aqueous ethanol. So this is nucleophilic substitution in which we will have the bromine atom replaced by the nitrile group. So the product would be CH3, CH, CN, and then CH3. So the halogen alkane is converted into a nitrile. And D going to E, we heat it under reflux with sulfuric acid. So this is acid hydrolysis, and acid hydrolysis results in the formation of a carboxylic acid. So the CN group will be converted into the COOH group. So this will become CH3, CH, COOH in the brackets, and CH3. So this is product E, a carboxylic acid, which is formed upon acid hydrolysis of a nitrile. Now, looking at F, that is the 2-bromopropane reacting with ammonia in excess. So this will result in the formation of an amine in which the Br will be substituted with NH2. So this is also nucleophilic substitution. So the product is CH3, CH, NH2, and then CH3. This is product F. And finally, 2-bromopropane reacts with NaOH in ethanol and heated under reflux. So if it was reacted with only NaOH, this would have been converted into an alcohol. But since we have ethanol also present, so this will be called dehydrohalogenation. The bromine atom from the central carbon and one of the hydrogen atoms from either of the two terminal CH3 groups would be removed, resulting in the formation of an alkene. So the alkene would be the same as the starting reactant. So this would be CH3, CH double bonded to CH2. So we ended up with the same organic compound that we started off with. Under suitable conditions, compound E will react with compound B. So the compound E is the carboxylic acid and compound B is the diol. What functional group is produced in this reaction? So when a carboxylic acid reacts with an alcohol, the functional group produced is an ester group. How is the reaction carried out in a school or a college lab? So we heat the reactants under reflux in the presence of HCl aqueous as catalyst. So heat under reflux with an acid. This will produce the ester, or we can actually use sulfuric acid, which would be a better acid to use here. So presence of HCl as a catalyst or presence of H2SO4 aqueous as a catalyst. So this will result in the formation of an ester when a carboxylic acid reacts with an alcohol. Question 7. Butanene is an important compound in the petrochemical industry. Some reactions of butanene are given below. In each empty box, draw the structural formula of the organic compound formed. So here we can see the entire organic synthesis pathway. So let us begin. We've got butanene on the left. Let's go in alphabetical order: T, U, V, and W. So on the left, we've got it reacting with steam and phosphoric acid in the presence of a catalyst. So we have formation of an alcohol. Now, the alcohol produced may have the OH group on the terminal carbon atom, or it may have the OH group on the second carbon atom. Now, this is electrophilic addition. So, the OH group being attached to the second carbon atom would be preferred because that would be a more stable alcohol than if the OH group was on the first one. So, both of the products would form, but the one with the OH group on the second carbon atom would be formed in a larger quantity. So that is the one that we are going to mention here. So that would be CH3, CH2, CHOH, and then CH3. This is compound T. For compound U, we've got hot concentrated acidified KMNO4. So that would result in breaking of the double bond completely, producing CO2 and H2O with respect to the carbon atom on the right side of the double bond. And the organic product on the left side would be CH3, CH2, and then the CH will be converted into COOH. So this will be propanoic acid. For compound V, we've got the same reaction, oxidation, but with under conditions cold and dilute. So cold dilute acidified KMNO4 or MNO4 minus ions would result in the formation of a diol. So that would be CH3, CH2, CHOH, and CH2OH. This is the diol, that is compound V. And when the diol is subjected to acidified Cr2O7 2 minus or K2Cr2O7 and heated under reflux, the central OH group, the one on the second carbon atom, would be converted into a ketone, and the primary alcohol group would be converted into a carboxylic acid. So the product W would be CH3, CH2, C double bond O, and single bonded to COOH. So this is a carboxylic acid with a ketone group present on it. Compound T reacts with compound U. So compound U is propanoic acid and compound T is butane 2-ol. Draw the discrete formula of the organic product of this reaction. So we start off with the propanoic acid. So that would be CH3, CH2, C double bond O, then single bonded to the oxygen atom of butanediol, which will be bonded to a hydrogen atom on one side and a CH3 group on the other. This will continue with a CH2 and ends up with a CH3, completing the structure of the ester. And if we are to name this ester, this would be called 1, 2, 3, 4. So it would be butyl, 2 butyl and 1, 2, 3 propanoate, 2 butyl propanoate, because we have got the oxygen atom present on the second carbon atom of butane 2 also, 2 butyl propanoate. Question 8. Food additives are substances added to food to preserve the flavor or to improve its taste and appearance. European Union legislation requires most additives used in foods to be labeled clearly in the list of ingredients, either by name or by an E number. E296 is malic acid, which occurs in unripe fruit. Malic acid has the structural formula given. So it has two carboxylic acidic groups and one alcohol group. Some reactions of malic acid are shown below. In the boxes below, give the structural formulae of organic compounds A to F. Here is the complete organic synthesis pathway for malic acid. So starting with A. So we are heating malic acid with CH3OH. Now CH3OH is methanol, and methanol would react with the carboxylic acidic group of malic acid and form esters. So we end up with a compound CH3, and then we've got O of CH3 and the O of malic acid, and then the carbon of malic acid, followed by CH2, CHOH. Then we've got C and O of malic acid, then the oxygen and the CH3 group of the methanol. So this is the diester that would be produced when malic acid reacts with methanol. Compound B is heat with CH3COOH, which is ethanoic acid. And here we would end up with another ester bond being formed, but this time the reaction would be of the OH group of malic acid. So the COOH groups would stay as they are. So HOOC for malic acid, CH2, CH for malic acid, then COOH. Then we would have the oxygen of malic acid. Then we would have the oxygen of ethanoic acid, the carbon of ethanoic acid, and the CH3 group of ethanoic present, forming the ester bond. So this is the product B that would form when malic acid reacts with ethanoic acid. Next, we have compound C, in which malic acid is reacted with concentrated sulfuric acid. So concentrated sulfuric acid is a dehydrating agent. So it will remove the OH group from malic acid and the hydrogen atom from the carbon on the left side of the structure drawn, because that is the only one having a hydrogen atom on it. So the OH group and the hydrogen group from the two adjacent carbon atoms would be removed, resulting in the formation of an alkene. So we would have HOOC, then we would have CH double bonded to CH, and then we would have another COOH group, and this alkene is compound C. The next reactions are of compound C. So when this compound is reacted with hot concentrated KMnO4, so the double bond would cleave. And now, since this is a symmetrical alkene, the product formed would be the exact same product. So we have formation of C double OH on one side and C double OH on the other side as well. So this is oxalic acid. So it is the organic product that is formed. However, just to note that oxalic acid undergoes further oxidation in the presence of similar condition or rather the same conditions and is converted into CO2 and H2O, but these are not the organic compounds. They asked us to mention the organic compounds produced, so we will mention oxalic acid or ethane 1,2-dioic acid, which is its systematic name. And we will not mention CO2 and H2O because product D has to be organic in nature. So oxalic acid or ethane 1,2-dioic acid is product D. Now, when product C reacts with steam and H3PO4, so this is the formation of an alcohol. So the OH group would be added to one of the carbon atoms having a double bond and the hydrogen atom on the other, producing the malic acid again. So the product is HOOC CH2 CHOH and then COOH. So we have obtained malic acid again, which is compound E. And for compound F, we have got compound C reacting with cold dilute acidified KMnO4. So this results in the formation of a diol. So we will end up with a compound having two carboxylic groups and two alcohol groups on the central two carbon atoms. So OH here and an OH here. So this is compound F, which contains two carboxylic acidic groups and two alcohol groups. What type of a reaction is each of the following conversions? Malic acid into C. C is the alkene, so malic acid into C is called dehydration. C into D. Now, D is the carboxylic acid, oxalic acid. So an alkene is being converted into a carboxylic acid on reaction with hot concentrated acidified KMnO4. So this is called oxidation. And the next is conversion of C into E. Now C is the alkene and E is the alcohol. So we have the reaction with steam and H3PO4, which is called hydration or addition reaction. So hydration of alkene to produce the alcohol. Suggest one major commercial use of compounds such as A and B. A and B are both esters, and the most common uses of esters are as flavoring agents, or we can have them as components of perfumes, or we could have them as solvents. These are the three most common uses of esters. Malic acid is chiral. Draw the fully displayed formula of the two optical isomers of malic acid. Indicate with an asterisk the chiral carbon atom. So, the carbon atom in malic acid that is chiral would be the one having an a hydrogen atom on it, a CH2 group on it, not CH2, CH2, COOH, a COOH group on it, and an OH group on it. So the two optical isomers will have two of these groups positioned at the same position, and the other two positions would be switched. So if we place a hydrogen atom here, so it will stay here, the hydrogen atom. Then we would have the OH group placed at the bottom, which would stay at the same position. Now, if we place a COOH on the left on one of the isomers, on the right, then this would be placed on the left of its optical isomer, and the remaining group would be CH2COOH on the left side of one isomer, which will be positioned on the right side of its optical isomer. So these are the two optical isomers of malic acid, and the question is asked us to mark the chiral carbon with an asterisk. So the central carbon atom is the chiral carbon atom here. Compound C also shows stereoisomerism. Now compound C is the alkene. Draw the skeletal formula of each of the stereo isomers of C and label each isomer. So isomer C is 4 carbon atoms with 2 COOH groups and 2 CH2 groups with a double bond between them. So they've asked us to draw the skeletal formula. So we have a double bonded carbon atom with a COOH here and a COOH here. This would be one of the stereoisomers, which is the cis isomer of compound C, and in order to make the trans isomer, we have the one of the COOH groups placed on the opposite side. So COOH here and COOH here. This is the trans isomer of compound C. And label each isomer. So we have labeled them cis and trans. The food additive E330 is another organic compound which occurs naturally in fruit. E330 has the following composition by mass of carbon, hydrogen, and oxygen. And calculate the empirical formula. So we would be needing the percentages. So carbon, hydrogen, oxygen. Percentage of carbon is 37.5. Percentage of hydrogen is 4.17. Percentage of oxygen is 58.3. So first we divide these by their AR values, which is 12, 1, and 16, which gives us a value of 3.13 for carbon, 4.17 for hydrogen, and 3.64 for oxygen. Now we divide them by their simplest numbers out of these three, which would be 3.13. So 3.13 divided by 3.13 divided by 3.13. So this would give us a carbon is to hydrogen is to oxygen ratio of 1 is to 1.33 is to 1.16. So in order to convert them into whole numbers, we would multiply these ratios by 6, which results in the number of carbon atoms being 6, the number of hydrogen atoms being 8, and the number of oxygen atoms being 7. Therefore, the empirical formula of this compound is C6H8O7. Question 9. Butene is an important compound which is obtained from the cracking of hydrocarbons present in crude oil. Give two different conditions under which long chain hydrocarbons may be cracked. So, cracking has two conditions. It is catalytic cracking, which requires Al2O3 or SiO2 as catalyst, and there is thermal cracking, which requires a temperature of 450 degrees Celsius or above. And if we are using the two together, we can have a high temperature and a catalyst. And if we are just using the temperature, we will also need a high pressure in order for the cracking to proceed. Dodecane C12H26 is a long chain hydrocarbon which is present in crude oil and which can be cracked to form butene and an alkane. Write a balanced equation for this reaction. So we have C12H26 undergoing cracking to produce butene. So the formula of butene would be C4H8. So if C4H8 is removed from C12H26, what remains is 12 minus 4 is 8, C8, and 26 minus 8 gives us H18. So C8H18 is octane, which is a component of petrol. So that is another useful fraction or one of the compound that is obtained due to cracking or lower fraction rather. A higher fraction alkane is converted into lower fraction more useful products. Some reactions of butene are shown below. In the boxes below, give the structural formulae of the organic compounds A to D. So, we've got butene reacting with hot concentrated acidified KMnO4. So, the double bond will be completely cleaved or ruptured. And since it's a symmetrical alkene, the same product will form. So, that product would be CH3 COOH, which is ethanoic acid. When butene reacts with chlorine, electrophilic addition will take place and a chlorine atom will be added onto each of the carbon atoms having a double bond. So the product would be CH3, CHCl, CHCl, and then CH3. And we can place the Cl in a bracket if we want. So this is product B, which is a dichlorohalogenoalkane. For product C, we've got butene reacting with cold dilute acidified KMnO4, which results in the formation of a diol. So this would be CH3, CHOH, CHOH, and then CH3. And when this compound is heated with acidified K2Cr2O7, oxidation will occur. And since both the alcohol groups are secondary alcohol groups, they will be oxidized into ketones. So this would become CH3, C double bond O, C double bond O, and then CH3. So two ketone groups will form from two secondary alcohol groups of compound C, forming compound D. Draw the skeletal formula of compound D. So compound D is a chain of four carbon atoms with a ketone group on the second and the third carbon atom. So this is the skeletal formula of compound D. By using the letters A to D as appropriate, identify those compounds which are chiral. If there are none, write none. So here is a look at the four compounds. Compound A does not have any chiral carbon atoms present. Compound B has one and two chiral carbon atoms present. Compound C will also have one and two chiral carbon atoms present. And compound D will not have any chiral carbon atoms present. So in total, we have two compounds with chiral carbon atoms present, which are compounds B and C. So we mention compounds B and C in the given space. Butene can be polymerized to give polybutene. Draw the structural formula of a portion of the polymer chain in polybutene. Show two repeat units. So, polybutene would have the C double bond C converted into C single bond C with both carbon atoms having a CH3 group on it and a hydrogen atom on the remaining position. And they've asked us to draw two repeat units of the polymer chain of polybutene. So we will have another set of carbon atoms, each having a hydrogen atom on it and each having a CH3 group attached to it. So these are two repeat units of polybutene. Compound C is a liquid which can be reacted with concentrated sulfuric acid to give gas E, which will decolorize aqueous bromine when passed through it. Suggest the structural formula of E. So compound C is a diol, and it says that compound C is a liquid which will react with concentrated sulfuric acid. So this is basically dehydration. So upon dehydration, we've got an OH group on the central two carbon atoms and the terminal carbon atoms having three hydrogen atoms. So this will form a compound with two double bonds in it. So it will be CH2 double bonded to CH, single bonded to CH, and then double bonded to CH2. So this is the product which will contain two double bonds, and this is an alkene, so it will decolorize aqueous bromine. Suggest the structural formula of the product of the reaction between E and an excess of bromine. So when E reacts with an excess of bromine, we have the formation of an halogenoalkane in which both the double bonds will be removed and bromine atoms will be added onto each carbon atom. So all four carbon atoms will be attached to a bromine atom. So the product would be CH2, CH, CH, CH2, and a Br atom on each of the carbon atoms. What type of a reaction occurs between E and an excess of bromine? So bromine is added onto the alkene. So this is known as an electrophilic addition reaction. So alkenes undergo electrophilic addition with aqueous bromine to produce a halogenoalkane or a bromoalkane. Here in this case, we've got a bromine atom attached to each carbon atom because there were two double bonds present in compound C.